Alright, this thing's working all poorly, so we're gonna have to write super small. Not super small, super slow. So inductive reasoning, which means we need to look at our data and come up with a pattern. So 1/2, 1/4, 1/8, 1/16. Well, the top number looks like it's going to stay the same, and the bottom number looks like it's doubling. So 32 and 64. That wasn't so bad. Alright, A, B, D, G, K. This looks like a pattern with the alphabet, so let's come up with the quick alphabet here. So A, B, C, I, J, K, L, M, N, O, P, Q, R, S, T, X, Y, Z. Okay. So let's find the pattern. So between A and B, that's plus 1 letter. From B to D is plus 2 letters. From D to G is 1, 2, 3. And from G to K is 1, 2, 3, 4. So based off of that, we can say that the next letter should be 5 away. So 1, 2, 3, 4, 5. So the next one should be P. And then 6 more after that is 1, 2, 3, 4, 5, 6, or V. Hooray. Okay. Number 2, write the first 5 terms of 2 different sequences that have 10 as the second term. So all this is meaning is we want to write a sequence where 10 is the second number. So we need a first number, a third, a fourth, and a fifth. So, I mean, there's an infinite number of patterns we could come up with. Basically, all we gotta do is pick a first number. Like I could say, I don't know, 4. And then I could say, well, this is plus 6. So I could do plus 6 all the way down the line. So this would be 16, 22, and 28. Okay, or we could do, I don't know, we could do 2 here. And we could just say this is plus 8, or we could actually say this is times 5. So we could just do times 5 all the way down. So 10 times 5 is 50. 50 times 5 is 250. And 1250. Oh, that's a 5. And that's it. I mean, yours don't have to look like that. If they do look like that, I'm just going to say you're cheating. Alright, number 3. Sequence using the description. First term is 4. Each term after that is 3 more than twice the previous term. Okay, so the previous term is 4. Twice as much of that is 8. Plus 3 more is 11. Okay. After that, if we double that number, so it's 22 plus 3 more is 25. And if we double that one, 25 times 2 is 50, plus 3 more is 53. And we'll give you bonus points if you come in tomorrow with an actual, like a rule for that, you know, with like n plus something. It's going to be a lot more complicated than that, but I trust you can do it. Maybe a few of you with help from an adult. Possibly. Okay. Number 4. Draw the next shape in the pattern. So what is the pattern? What is it?
What pattern?
The pattern.
It's Y shapes.
Okay, then what?
Then it breaks up into more Y shapes.
Very good. Alright, if the old lady can get it, then all of you should have gotten it. Yeah. So all it is it just like a snowflake or some sort of weird, almost fractal-like thing? It's just going to keep breaking up into the same pattern, which means our next one should look just like this. So we're going to draw our original Y, split up, and then split again, and then each of these would have to split one more time. So, dun, dun, dun. Ugh, this is ugly. It looks like a tree. Wait, I'm messing this up. Whatever. This should be turned around more. And that looks awful, but you get the idea. I could have. It is a tree, an ugly tree. Pretty unique. Yeah, I wouldn't call it pretty and unique though. Draw the next shape. Done. Write a sequence of numbers that could be used to describe the pattern. Okay. So if we look at the number of ends of our tree, our first one had 2. Our next one had 4. Our one after that, take a guess. It has 4, 5, 6, 7, 8. Which means this one here, I'm not going to count them all, has 16. So the sequence of numbers, it's always going to be times 2. Okay. And verbally describe the pattern of the sequence. So it's like a tree, it continues to branch. Every branch gets 2 new branches on the next shape. Actually, it's not times 2. Why would I say times 2? I mean, each one is 2 times more than the previous, but if we made a chart out of this, where n is the shape numbers, which would be 1, 2, 3, and 4. 1, 2, 3, 4. And I don't know what we're going to call this. We'll call it y. It goes 2, 4, 8, 16. So if you think back, we talked about this a little bit at the end of last year about how this pattern comes about and how it relates to this here. And it wasn't actually 2 times the number, because that stops working right here. 3 times 2 is definitely not 8. 4 times 2 is definitely not 16. So we look at a different way. How do we show that each time we're just multiplying by 2 again? So it's not, what is kind of times 2 in a way? So what it is we're taking n, no, we're not taking n. We're taking the number 2, that's our key number, and it's 2 times itself n number of times. Like 2 one time is 2, 2 times 2 is 4, 2 times 2 times 2 is 8, 2 times 2 times 2 times 2 is 16, so it's just our pattern is 2 to the nth power. Okay? And if you forgot how to do that, then watch the old videos because it's probably on there. Right? Probably. Use expressions for even and odd integers to confirm that the product of an even number and an odd number is even. Okay. I guess we can do that. So, even times odd should be even. So, 4 is even times an odd equals an even. Success! Let's try again. 2 times 5 equals 10, which is even. Success again. Why does this work? Hey, language.
I can't hear me.
Yes, I can.
No.
After I said language, they're going to rewind it and turn the volume up really loud. Pretend you didn't hear that. Okay. Evens and odds? Yeah. So what this comes down to is, say we have an odd number of things. Like, what things we want to add? Quick. She's walking away. Let's add ducks. I like ducks. Oh, I don't have ducks. All I have is these 15 ducks. Hold on. I'm going to go find ducks. Wait here. Alright. Fear not, we found some ducks. So let's look at why this works out so wonderfully. So let's say we have 3 ducks, yeah? And we want 4 groups of these 3 ducks. So we're going to copy it and then pop, pop, pop. Now we have 4 groups of, oh no, bad duck, bad. Okay, one more. Okay, so this is our 12 ducks. We established this. 4 times 3 is 12. That's not the question here. So what does this have to do with evens and odds? So let me tell you. If we just had 2 groups, if we just looked at these here, this is 3 ducks plus 3 ducks. And we said earlier in the chapter that an even, or no, sorry, that an odd number plus an odd number will always equal an even number. Even. I don't like this thing. Even. Okay? So we're partway there. So we can take, since this is even, we're always going to have an even number of groups because that's the point. It's odd times an even. So this is going to be an even number of groups. So all these individual groups will always total up to an even number. So these smaller groups of 2 will always be even. Odd plus odd always equals even. And we're always going to end up with an even number of these purple boxes, which means that when we add these up, it's going to be an even number plus an even number. And even plus even always equals even. I've forgotten what the word even means. Have you ever done that when you say a word so many times and it starts to sound weird? You just keep saying even, even, even. Suddenly it's like, I think I have a cousin named Even. It used to be Steven, but now everything's even. Okay, whatever. So that's why this works out. Okay. There's probably other ways to explain this, but I like my ducks. Okay, so suppose you're given first 5 terms of a sequence. What are approaches you can determine the rule for the sequence? And then write the next 2 terms. You may use an example. Okay. Well, we have an example. We did this already. So why can't I click you? Okay, whatever. I'm gonna look at this example right here because this isn't working. So here's our sequence of 5 terms. What can we use to figure it out? Well, what we've always used since 7th grade is we use this idea of common differences. I have to write so slowly, otherwise this doesn't work. Okay, we've always used common differences. And by looking at that, we look at the change in the sequence, we can establish a pattern, and we can make a rule based on that pattern. Like this one here for a common difference is 6. That means part of our rule is 6n, right? And then we can test it like we've done, like we'd say 6 times 1 to try to get this value. But 6 times 1 is 6, so how do we get to 4? What about 2?
You have to multiply it.
To get from 6 to 4?
You have to subtract it.
There you go. So we could say 6n minus 2. Thanks for the assist. High fives. No louder. They can't hear you. Yeah. All right. The other way we looked at it, we didn't talk about it that much because it's sort of unnecessary. Is to actually look at the 0 term. So if we actually step back, if we took 6 away from 4, we'd actually end up at -2. And look, -2, that's what we put here. So that's another possible strategy is common differences always. This is the big mama of sequential rule finding. And then the 0 term can use to help find any leftover stuff. Okay? So I think that about answers that question about as well as I feel like answering it. If you put other stuff, I'm proud of you. If you put what I wrote, I'm okay with that. And if you leave it blank, then you were too lazy to listen to this part. But if you didn't listen to this part, you didn't hear this part. Who am I talking to? Oh well. Alright, good night. Like, comment, and
Reply?
so subscribe, Katie.
Oh.
Subscribe.